This is Transformations of Graphs of Linear Functions, Part 1. And we're going to start with some vocabulary. We're going to be looking at different families of functions. A family of functions is a group of functions with similar characteristics. Within each family, there is a parent function, and that is the most basic function in the family. A transformation changes the size, shape, position, or orientation of a graph. And we're going to be looking at some transformations of our families of functions. One transformation we're going to look at is called a translation. A translation is a transformation that shifts a graph horizontally or vertically. We're also going to be looking at a reflection, which is a transformation that flips a graph over a line, which is referred to as the line of reflection. Let's see some of these things in action. So we're going to first look at horizontal translations and vertical translations. So we start off with a parent function, which is called y equals f of x. And I've graphed y equals f of x on both of these graphs. Now when finding y equals f of x, I'm taking my input, plugging it into the problem, and I'm getting an output. Those become my coordinate points. Now if I take my input and I subtract a number from it, it is going to horizontally translate my graph. If the number that I subtract from my input before plugging it in is greater than 0, my graph will shift to the left. If the number that I subtract from my input is less than 0, and then I take that and plug it into my function, it's going to move the graph to the right. To get a vertical translation, I'm going to take my parent function, plug in an input, get my output, and then I'm going to add a number, which I'm calling k, to my output. So here's my parent function. When I get my output, if I add a k that is greater than 0 to my output, it's going to move my graph up vertically. If I add a number k that is less than 0, it's going to move my graph down vertically. Now, this h can't be exactly 0 in this one because I will get the exact same parent function. And the same thing here. K can't be exactly 0 or I'm just going to get the parent function over again. So let's see how this works. Always makes more sense to me when I see a real example. So here I've got a parent function, f of x equals 2x minus 1. And I've made two graphs where I've put the parent function on the graph. Now how did I get these coordinate points? I plugged in some inputs. So I plugged in 0, 2 times 0 minus 1 gave me negative 1. So I put the point 0, negative 1 on my graph. I plugged in 1, 2 times 1 is 2, minus 1 is 1. So 1 comma 1 was a point on my graph. I plugged in 2. 2 times 2 minus 1 gave me 3. So 2 comma 3 was a point on my graph. I plugged in negative 1. So 2 times negative 1 was negative 2. Minus 1 was negative 3. So negative 1, negative 3 was on my graph. So you get the idea of how I got these points. And then I put my parent function on both graphs here. Now on this first graph, they're asking us to graph g of x, which is going to be my f of x problem plus 3. So when I did my f of x and I put in 0 as my input, I got negative 1 as my output. If I take that output and I add 3 to it, I'll now have 0 comma 2. When I put 1 in here, I got an output of 1. Now if I take that output and I add 3 to it, I get 4. So 1 comma 4. Let's try one of the negative ones. So when I put in negative 2 here, I got an output of negative 5. Negative 5 plus 3 would be negative 2. Now if I connect these points, I'm getting a line that is parallel to my parent function, but it has vertically, everything has moved up 3 spaces. So this is a vertical translation here, with everything moving up 3 spots. Let's look at another example. This time we took our parent function and they're asking us to graph t of x, which we're going to take our input and add 3 to it before we do our function. So if I had 0 as my input, 0 plus 3 is now going to be an input of 3. 2 times 3 is 6, minus 1 is 5, so for 0 I get an output of 5. Let's say negative 2 was our input. Well, negative 2 plus 3 is now 1. 2 times 1 is 2, minus 1 is 1, so for negative 2 I get 1. Let's try 1. So my original one I would plug in 1, but 1 plus 3 is now 4. 2 times 4 is 8, minus 1 is 7, so for 1 I get an output of 7, right up there almost off my graph. So if I connect these, I get a line that is parallel to my parent equation, but every point has moved over horizontally. So everything has moved horizontally 3 spots. So this is a horizontal translation. Another type of transformation that we're going to look at is a reflection. So a reflection in the x-axis is when we have our parent function and it flips over this x-axis. Our x-axis becomes our line of reflection. So the original parent function was y equals f of x. If I take the opposite output, y equals negative f of x, I'm going to get that reflection over the x-axis. If my parent function is y equals f of x, and I take the opposite input in my function, I'm going to get a reflection over the y-axis. So this y-axis becomes my line of reflection. Sometimes when I'm doing these problems, it's very difficult to do a lot of work in my head, so I like to make a table for myself. So that's what I've done here. My parent function is f of x equals 1/2 x plus 1. So I made a little chart and I picked some random x's to be my inputs and I plugged them into my parent equation. So I plugged in negative 4. Negative 4 times half was negative 2 plus 1 gave me negative 1. Negative 2 plugged in there. Negative 2 times half was negative 1 plus 1 gave me 0. I plugged in 0. Half times 0 is 0 plus 1 gave me 1. And I graphed those points and connected the line to put my parent function on both of these graphs. Now, in order to do my reflection here, they're asking me to graph g of x equals negative f of x. So an opposite output. So here my output was negative 1. The opposite output would be 1. 0's opposite output would still be 0. 1's opposite output would be negative 1. So I'm using the same input. Negative 4 comma 1 is my new point though. So negative 4 comma 1. Negative 2, 0, right here, that's the same point on both graphs. And 0, negative 1. And if I connect these points, I notice that I have just reflected my line over the x-axis. So this is a reflection over the x-axis. All right, so once again, I'm starting with my parent function. This time though, I'm being asked to do the opposite input. So my original input was negative 4. If I flip that input, it would be 4. 1/2 times 4 is 2, plus 1 is 3. My input of negative 2's opposite would be 2, and if I plug 2 into my original equation half of 2 is 1, plus 1 is 2. And if I plug in 0, 0 times half is 0, plus 1 is still 1. So let's try plotting these points. So -4, 3, -2, 2, and 0, 1. This one's the same point on both. And if I connect them, I have this time a reflection over the y-axis.